Thank you very much for asking you to join your International Advisors panel and also inviting me to give you this presentation. I'm going to perhaps change the pace a little bit. I'm going to focus on what we call sustainable development. Let me see if I can get my slides to it. So in sustainable development is a relatively new development that is coming out, actually spreading all across the world. And generally, like all new technologies, sustainable development today means do an R&D product development and then just add some sustainability parameters to it to make it sustainable. That doesn't work. And I'll tell you why. In this presentation, I will define sustainability to include both environmental sustainability, but also economic and cultural sustainability. That's why most R&D programs do not have the stamina to go ahead and actually transform the society from which the R&D program is supported because it's not sustainable. And so our challenge is to start R&D programs that are not only high quality, address real problems of the society, but are also sustainable for the long term. So let us first look at the key prerequisites of a sustainable program. One, for example, public health. As you will see, in analysis that has been done recently, public health is the greatest factor that controls productivity and development in a society. Healthy vision care is a key component of the good public health, and I will be focusing my examples on vision care. Among vision care, uncorrected refractive errors, cataracts and aphakia, which is the loss of the natural lens of the eye, are the three most prevalent causes of loss of vision in developing countries. I will present two case studies that will show you how products developed to meet the same basic health vision care need, but designed for different communities, acquire two completely different designs, and therefore require different manufacturing processes and different distribution and supply chain management. So in both cases, these innovative products were developed from cutting-edge science and developed through collaboration with multinational teams. But they are only part of the story. As you will see, these products developed with contribution and input from the communities disrupted existing supply chains in these countries. And I will give examples from Africa, China, and India, put consumers and community workers in control. And the result was an explosive growth in the number of treatments, transfer of pricing control to local caregivers, allowing them to pursue this growth model. And finally, I will show you a multi-stage sustainable product development model that was developed from these initial results. So what are the key success requirements for a sustainable program? It's excellence in science as well as technology, because it's the science that's necessary to change the path of technology development and develop transformative solutions. Adoption of local health needs as a strategic driver of development. Collaboration with and learning from local caregivers and local industry. And look at the emphasis on the initial stage of product development. That is that we get these inputs from the community and local needs up front when the product design is taking place, not later during the product development process. And then we achieve scale by increasing the level of community involvement all across the country, that is doing many parallel starts, as opposed to a vertical integration scale up, automation, etc. So Dr. Shahzad Alvi did a study introducing a factor-based model of productivity in a country by analyzing what are the key quality of life parameters that that control productivity. And he found that health was by far the biggest driver, not GDP. So this is why we decided to focus on public health, particularly my area of specialty, vision care, in understanding and how to develop a sustainable R&D model. So here is an example of a sustainable R&D program model that was presented. This was developed at the Fraunhofer Institute in Germany, presented in France, 2012. Note that there are some global sustainability parameters, but there is no mention or no account is taken of local needs or community requirements. So such a cut and paste R&D sustainable program cannot last. Here is another model that was developed and included in the Global Sustainable Development Report in 2015. Here, consumer needs and community interests are coming in indirectly through the introduction of innovation, both development of innovation and its diffusion into the community. But still, the product design, there is no explicit accounting of community leaders and consumers in creating innovation. So we see, therefore, that there is a need to develop a truly sustainable R&D development model. And so I'll show you two case studies, both in vision care. So let's begin with what the magnitude of the problem of vision care is globally. 3 billion people, 45% of the world's population, require some sort of vision correction. Poor vision is a development issue as well as an educational issue, because development issue in the sense that it saps productivity. Development issue in the sense educational issue because it deprives children of the opportunity to learn and therefore become productive individuals. Significant vision impairment due to uncorrected distance or near vision affects 84 million people globally. And blindness affects approximately 39 million of those 284 million who are impaired, 39 are blind. So we are looking at vision care, we are looking at one of the major public health issues that exists in all countries, at all levels of development. So here is the first product. Dr. Joshua Silva developed a product called AdSpace. The idea was to develop an adjustable eyeglass that could be given to people in developing countries who has inadequate support from the local health professionals, and allow them to adjust the eyeglasses so that they could read without any further help. Okay? So the adjustable eyeglasses look like this. They consist of two lenses. They consist of two membranes sealed to form a space filled with oil. There's a syringe there that has more oil in it. The person who wants to have his vision care corrected wears these eyeglasses, adjusts the syringes until the lens has the right power for them to see. In other words, the person self-refracts, produces correction, and at that point, the syringes are removed. producing an eyeglass that looks like this. Okay? Over 40,000 pairs have been distributed throughout the world, and the data show that self-refraction is easy to learn, train, and teach without direct support from professionals, and it's safe and effective. Okay? This product was tested in remote north of Ghana, and this was a study of about 800 people, 800 subjects. The results were published here. Sorry. There we are. So here is another study that was done with these AdSpace in rural China, 600 children. They had powers, uncorrected powers going from -10 to 2.5 diopters. For good reading, you want a power of 0 plus or minus 0.5, preferably 0. And you can see that after self-adjustment, their power came down to somewhere between 0 plus or minus 1. And in fact, about more than 80% of the children had power 0 plus or minus 0.5, good enough for 20, 30 or better vision, effectively functional vision, covering 90% of the population. So this shows that the importance of being able to see an optometrist and having the product dispensed by the optometrist is not essential for this product. While that was going on, simultaneously, another product was being developed in the United States. This was called the first adjustable strength reading glasses. This was designed for consumers who wanted something better than current reading glasses in advanced countries. The idea was to develop a pair of reading glasses with adjusting knobs on both sides until the power was adjusted for the wearer to be able to see at any distance. So for example, when somebody is working on a computer, they need lower power because the computer screen is farther off. While somebody is looking at a medicine bottle, they need higher power in order to magnify those tiny letters. These reading glasses managed to do that by adjusting the power over 1.5 to 3.5 diopters. And as you'd expect, there was a need to develop more feminine styles, different styles of frame, metal frames, and all of these products added number of SKUs, different colors, different shapes of optic in order to produce a non-round liquid-filled optic that's adjustable power. We had to develop highly sophisticated optical design of this system, and that had to be implemented with high-precision optical injection molding. But all of that was done, and these products could be developed. And you can see that the visual acuity of this product, the non-round product, was better than the leading brands of reading glasses. So the visual performance of this product was just as good as the visual performance of the product that Dr. Silver developed for the impoverished children and people who had lack of access to conventional vision care professionals. So here is a further example of how this product could be taken even more high-tech. Here now we have little batteries, piezoelectric drivers that adjust the distance and thereby change power automatically. So here is the difference of these two products that you see are meeting the same basic healthcare need, vision correction, driven by two different types of needs and two different types of communities, for two different types of communities. And here, this is for underserved population in developing countries. This is a high-end product for emerging presbyopes in developed countries. Give them something better than what they have today. Round shape provides uniform thickness, best optics, lowest cost. Just all we need are sheets of mylar. Non-round optics, the membrane now has to have dimensional anisotropy to correct for spherical aberration, astigmatism when optical power is altered, and therefore the design is highly complex, and therefore precision injection molding is required. Single stock to reduce cost of manufacture and inventory, multiple SKUs. Distribution directly through government agencies, community organizations. Here we use normal channels, optometrists and major optical outlets. Cost of production, $1 a pair, $13 a pair. Target price, $250 a pair. Target price to consumers, $80 to $100 a pair. So you can see that the two products, they are both valid solutions, design solutions to different needs. And if, for example, we try to introduce, modify to underserved populations by trying to make it simpler and cheaper, it would not work. Just as if we tried to sell AdSpace into developed countries where they wanted something better than their current reading glasses, it would not work. So this is why the needs of the consumers, users, and the communities where they will be used have to be taken into account up front. So here is some further examples. This is the modify, excellent visual acuity needs, and here we have, they both cover 90% of the vision correcting population's needs. And in one case, we go through optometry shops to provide selection, superior customer service. On the other hand, here, this product does not really need the intervention of a professional, although obviously it can be distributed by optometrists. So let me go to the next example, and this involves a device to correct cataracts. After cataract surgery, this is a device that's implanted to restore vision. It's called an intraocular lens. 284 million people, as I just mentioned, are visually impaired. Of these, 39 million are blind. And cataracts are the first main cause of blindness and visual disability, followed by refractive errors. Here is the example of what a major healthcare problem this is. So we have in the United States right now approximately 25, maybe about 27 million people who have cataracts that have not had cataract surgery to restore vision. The number of cataract surgeries per year, as you can see, goes from 3.3 million to India is one of the exceptions, and you will see why. 4.1 million. I'll show some statistics to show you why India has made such a high level of progress relative to, for example, China and the rest of the world. Okay. So here are the two products, and I was fortunate enough to be involved in development of both of them. One is a conventional intraocular lens, excellent optics, restores vision. It is foldable. It's made of a flexible plastic, foldable, so that it goes through a small incision because the incision into the eye is small, the healing process is much faster, and post-surgical trauma and complications are much less. So introduction of small incision surgery has required these lenses to be flexible so that they can be folded before implantation. Here is a second type of a foldable intraocular lens. Here the goal is to not only provide a fixed optic to restore vision, typically for far vision, but a dynamic optic that changes power electronically so that when the wearer or the patient sees near, there are sensors, embedded sensors, that sense the near vision process, adjust power into of the lens, and therefore without any activity by the patient, the power changes. So we designed such a lens, dynamic power change, electronic settings are customized for each patient, regular monitoring and adjustment, significantly higher fabrication cost. It contains all of the essential components of a controlled, autonomous, controlled remote system that's installed and it can be communicated with from outside wirelessly, but in general, it's supposed to be independent and fault tolerant. And it has the usual battery to provide power source, sensor, RF antenna that provides power, okay? So these are the two products. One developed for patients who want to go beyond restoration of vision for cataract surgery, after cataract surgery, and are willing to pay for it. And the other one for underserved populations who desperately need cataract surgery and an intraocular lens that can restore their vision. So to give you an example of the magnitude of some of the scale of some of these eye care centers, I want to show you this statistic. Arvind Eye Hospital in South India performs 401,000 surgeries per year in one site, which means that they do about 1,500 surgeries per day. So going there is an experience for me. I was absolutely amazed at the dedication and the hope among thousands of patients. The waiting room in this hospital was a field, like a football field, because there are 10,000 people waiting in the waiting center room to have their surgery done. So this is the hospital. 20 million people have so far had surgery in Arvind. Now, Aurolab is the R&D development arm of Arvind Eye Hospital. So Aurolab teamed up with a group called Project Impact, which was established by Mr. David Green, who developed a unique approach to sustainable R&D. The philosophy of Project Impact is that it is not just about reducing costs. It's about changing the business model in order to reduce price. Understand the political environment in which the status quo of high pricing, lack of competition and transparency can live and thrive in order to formulate disruptive interruptions. Use price as a weapon to change the competitive landscape in a given industry, and this is what they did, Aurolab and Project Impact did in India. This is a needle with a suture. The manufacturing cost globally is $240. Arvind makes it for 10. The intraocular lens, typically about $100, $150 manufacturing price. Aurolab makes it for $2. The total direct and indirect costs, Arvind Eye Hospital for each cataract surgery was $29. Arvind's outcome rivals that of any leading US hospital in ophthalmology. So their outcome is just first rate. So here is an example of their production facility. They machine their intraocular lenses on a series of precision lathes, diamond turning machines, because these are non-spherical optics. And here is how Arvind managed to introduce intraocular lenses as they became developed, because initially they tried to do this by purchasing intraocular lenses from the open market and found that it was too expensive, because the cheapest intraocular lenses you can buy go from $150 to about $2,000. That's the price range, and that would not allow them to pursue the kind of healthcare provided that they are doing. And so this introduction rate of intraocular lenses parallels their production, low-cost production. So this is how the cataract treatment market grew in India over about 5-year period. So now let's go to the premium product. In the premium products, we have, these are the various types of intraocular lenses that are used in developed countries. We have multifocal intraocular lenses and what we call accommodative intraocular lenses. They both provide both far vision and near vision, except that accommodative IOLs change power dynamically inside the eye. And there are two ways that you can make an IOL change power dynamically. One is by harvesting mechanical energy of eye tissue inside the eye. We call it mechanical accommodation. And the other one is the one that I just showed you, which is an electronic accommodation induced by electronic sensing of the desire for near vision. Here is a picture of this autofocusing intraocular lens. It has a sensor that picks up a physiological trigger, has onboard electronics, has two ASICs. One is to do power management, and the other one is to do data management. This has onboard logic, firmware, and embedded software, which senses the physiological signal, and this signal is extremely noisy, so there is a lot of signal processing going on, and after that, there is a decision made, and all of this is done by an algorithm that's embedded in the software. There is an onboard power source, battery. There is a RFID chip to have both data and power exchange from outside unit, and there is a memory and an external unit to recharge the batteries, receive data, and reprogram the software portion of the electronics of the software system inside the IOL. Here is how a typical assembly takes place. You can see that there's the batteries. This is the coil, RF coil that transmits the data and receives energy. Here are the two ASICs, the medical chip and the power chip. Here is the liquid crystal optic that changes power. Here are three wafers, PV cell that senses physiologically when the person is trying to look near, because when we try to see near, our pupils constrict automatically. is something that is completely hardwired in our brain. And it is this pupil motion that's picked up by PV cells, which are linear. There are PV cell line here, and there's a spot here. These are PV cells that pick up that change in light intensity that is going through the pupil and thereby activates basically produces a trigger for the medical chip to provide the actuation signal to the electroactive optic. Okay? So comparing these two products, it's foldable, the Orolab IOL that costs somewhere between $1 to $2 per unit. Foldable allows small incision. Biocompatible allows the use of latest surgical techniques, excellent visual outcome, far vision only. Patient needs to wear spectacles. Cost of manufacture, $1 to $2 per unit. Cost to patient, $5 to $10. This one is also foldable, allows small incision, it's biocompatible, requires a special inserter, like many premium IOLs, excellent visual outcome expected, aberration corrected optic design, accommodating, cost of manufacture, $80 per unit, cost to patients, I have been told by ophthalmologists that patients would pay $5,000 per unit, but let us say $2,000, right? So based on these two case studies, this is the kind of product development model that I think one could begin to develop for a truly sustainable R&D. And that's that one has to start with user needs and community needs, which are not necessarily the same. That defines product requirements, which then goes into design concepts, which then ultimately leads to what we call preliminary design specifications by selecting design concepts. And this testing can be done both bench testing as well as discussions with medical experts. And finally, we build a crude prototype, then a refined prototype, final product specs, and then we can manufacture. But ultimately, this design iteration process has to go back and affect or influence product requirements, which are again then controlled by community and user needs. So these needs are taken into account at every stage of this product development. Okay? This is, we believe, is how a truly sustainable R&D program can be established. So I will just end with a few acknowledgements. I acknowledge Mr. Sriram, the Director of Research or Operations at Orolab, David Green, founded Project Impact, MacArthur Prize winner, Professor Joshua Silver, and my friend Joel, who's a volunteer currently at Google X, colleagues at Helbling Technique, a Swiss engineering R&D organization, helped us add lens beacon and Elenza, and thank you very much.